Good day, everyone. I am Reina Maridi Bisaya, and I'm going to discuss the infinite series of positive and negative terms. In this lesson, you will explore infinite series with positive and negative terms, including alternating tests, where the signs of the terms change between positive and negative terms. You will understand how the alternating series test is used to check their convergence and learn the difference between absolute and conditional convergence, which show how the signs and order of terms affect the behavior of a series. You will also study the ratio test and root test, which are used to determine convergence or divergence in series that involve powers, factorials, or exponential terms. But before that, let us have our learning outcomes. At the end of the lesson, you will be able to first, determine whether a given series is alternating, absolutely convergent, or conditionally convergent using appropriate convergence test. And second, identify the properties and conditions that characterize alternating series, absolute convergence, and conditional convergence. And third, apply the ratio test and root test to analyze the convergence or divergence of the given series. Definition for alternating series: if a sub n is greater than 0 for all positive integers n, then the series the sum of negative 1 raised to n plus 1 times a sub n from n is equals to 1 to positive infinity equals a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 plus until negative 1 raised to n plus 1 times a sub n, and the series the sum of negative 1 raised to n times a sub n from n is equals to 1 to positive infinity is equals to negative a sub 1 plus a sub 2 minus a sub 3 plus a sub 4 minus until negative 1 raised to n times a sub n are called the alternating series. For illustration 1, an example of alternating series in form 1 where the terms is positive is the sum of negative 1 raised to n plus 1 times 1 over n from n is equals to 1 to positive infinity equals 1 minus 1 half plus 1/3 minus 1/4 until negative 1 raised to n plus 1 times 1 over n, and so on and so forth. An alternating series in the form 2 where the first term is negative is the sum of negative 1 raised to n times 1 over n factorial from n is equals to 1 to positive infinity is equals to negative 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus until negative 1 raised to n times 1 over n, and so on and so forth. A test sometimes used to test an infinite series of positive and negative terms for convergence is the alternating series. Theorem of alternating series. Let a sub n is greater than 0, the alternating series, the sum of negative 1 raised to n plus 1 times a sub n from n is equals to 1 to positive infinity, and the sum of negative 1 raised to n times a sub n from n is equals to 1 to positive infinity converge when these two conditions are met. First, the limit of a sub n as n approaches to positive infinity is equals to 0, and a sub n plus 1 is less than or equal to a sub n for all n. We have here our example 1. Determine whether the series is convergent or divergent. The sum of negative 1 raised to n plus 1 over n plus 1 from n is equals to 1 to positive infinity. So the given series is an alternating series of the form the sum of negative 1 raised to n plus 1 times a sub n from n is equals to 1 to positive infinity, where a sub n is equals to 1 over n plus 1. So for the condition 1, let us check if the limit of a sub n as n approaches to positive infinity is equals to 0. the limit of 1 over n plus 1 as n approaches to positive infinity, so equals the limit of 1 over n plus 1 as n approaches to positive infinity. So we need to evaluate the limit. So n is equals to positive infinity. So 1 over positive infinity plus 1. So that is equals to 1 over positive infinity, which is equals to 0. So the first condition of the alternating series is satisfied. Now let us check the condition 2. Check if a sub n plus 1 is less than or equal to a sub n for all n. So a sub n plus 1 is equals to 1 over n plus 2 and a sub n is equals to 1 over n plus 1. Since n plus 2 is greater than n plus 1, we have 1 over n plus 2 is less than 1 over n plus 1. So a sub n plus 1 is less than or equal to a sub n for all n greater than or equal to 1. Thus, the second condition is satisfied. Since both conditions of the alternating series are satisfied, therefore the series converges. For example 2, we have determined whether the series is convergent or divergent. The sum of negative 1 raised to n plus 1 times the square root of n over n plus 2 from n is equals to 1 to positive infinity. The given series is an alternating series of the form the sum of negative 1 raised to n plus 1 times a sub n from n is equals to 1 to positive infinity, where a sub n is equals to the square root of n over n plus 2. Let us check the first condition. Check if the limit of a sub n as n approaches to positive infinity is equals to 0. We're going to treat n as a continuous variable x. So the limit of the square root of x over x plus 2 as x approaches to positive infinity. The limit of the square root of x over x plus 2 as x approaches to positive infinity. So we need to evaluate the limit. X is equals to positive infinity. So the square root of positive infinity over positive infinity plus 2 is equals to positive infinity over positive infinity. So as you can see, we need to apply the L'Hopital's rule. So we need to get the first derivative with respect to x. The square root of x is equals to d over dx, x raised to 1/2. So apply the power rule, 1/2 x raised to negative 1/2. So 1 over 2 square root of x. So the denominator x plus 2, the derivative of x plus 2 is equals to 1. So the limit of the square root of x over x plus 2 as x approaches to positive infinity is equals to the limit of 1 over 2 square root of x over 1 as x approaches to positive infinity. Evaluate the limit. We have 1 over 2 times the square root of positive infinity. So 2 times the square root of positive infinity is equals to positive infinity. So 1 over positive infinity is equals to 0. So the first condition of the alternating series is satisfied. Now let us go to the second condition. Check if a sub n plus 1 is less than or equal to a sub n for all n. Consider the function f of x is equals to the square root of x over x plus 2. So we need to get the first derivative. F of x is equals to the square root of x over x plus 2. So applying the quotient rule, we have f prime of x is equals to the quantity of x plus 2 times 1 over 2 square root of x minus square root of x times 1 over the quantity of x plus 2 squared. So we need to simplify the numerator. So our numerator, x plus 1 over 2 times the square root of x minus the square root of x. To combine terms over common denominator, which is 2 square root of x. So 2 minus x over 2 square root of x. So our final derivative of our function is equals to 2 minus x over 2 times the square root of x times the quantity of x plus 2 squared. For x plus 2, f prime of x is less than 0, so the function is decreasing for x greater than or equal to 3. Thus, a sub n plus 1 is less than or equal to a sub n for n is greater than or equals to 3. Since both of the alternating series are satisfied for n is greater than or equal to 3, therefore the series converges. When the alternating series does not apply, so let us have example number 3. Determine whether the given series is convergent or divergent. The sum of negative 1 raised to n plus 1 times n squared over n squared plus 4, from n is equals to 1 to positive infinity. So the given series is an alternating series. So we let n is equals to 1, 2, 3, and 4. So the sum of negative 1 raised to n plus 1 times n squared over n squared plus 4 from n is equals to 1 to positive infinity is equals to negative 1 raised to 1 plus 1 times 1 squared over 1 squared plus 4, which is equals to 1/5, minus negative 1 raised to 2 plus 1 times 2 squared over 2 squared plus 4, which is equals to 4 over 8, plus negative 1 raised to 3 plus 1 times 3 squared over 3 squared plus 4, which is equals to 9 over 5, minus negative 1 raised to 4 plus 1 times 4 squared over 4 squared plus 4 is equals to negative 4 over 5, where a sub n is equals to n squared over n squared plus 4. So for condition 1, we need to check the limit if a sub n is equals to 0. So the limit of n squared over n squared plus 4 as n approaches to positive infinity is equals to the limit of n squared over n squared plus 4 times 1 over n squared over 1 over n squared. So n squared times 1 over n squared is equals to 1. N squared plus 4 times 1 over n squared is equals to 1 plus 4 over n squared. So from that, we need to evaluate the limit. So 1 over 1 plus 4 over positive infinity squared. So 4 over positive infinity squared is equals to 4 over positive infinity. So 1 over 1 plus 4 over positive infinity. And 4 over positive infinity is equals to 0. So 1 over 1 plus 0 is equals to 1 over 1 or 1. So the limit of n squared over n squared plus 4 as n approaches to positive infinity is equals to 1, which is not equals to 0. So the first condition of the alternating series is not satisfied. So let us check the condition number 2. Check if a sub n plus 1 is less than or equal to a sub n for all n. So consider the function f of x is equals to x squared over x squared plus 4. So we need to get the first derivative. So f of x is equals to x squared over x squared plus 4. Applying the quotient rule, we have f prime of x is equals to the quantity of x squared plus 4 times 2x minus x squared times 2x over the quantity of x squared plus 4 squared. Simplify the numerator, we have 2x cubed plus 8x minus 2x cubed over the quantity of x squared plus 4 squared. So the final answer is 8x over the quantity of x squared plus 4 squared. Since f prime of x is greater than 0, for x greater than 0, the function is increasing. So a sub n plus 1 is greater than a sub n. You cannot apply the alternating series test because the series does not satisfy the first condition. In fact, because the limit of a sub n is not equals to 0 as n approaches to positive infinity, the series diverges the nth term test for divergence. We have the alternating series remainder. For a convergent alternating series, the partial sum S sub n can be useful approximation for the sum S of the series. The error involved in using S approximately S sub n is the remainder R sub n is equals to S minus S sub n. So the theorem of alternating series, if a convergent alternating series satisfies the first condition, a sub n plus 1 is less than or equals to a sub n, then the absolute value of the remainder r sub n involved in approximating the sum s by s sub n is less than or equal the first neglected term. So that is the absolute value of s minus s sub n is equals to the absolute value of r sub n, which is less than or equal to a sub n plus 1. We have the example number 4. Approximate the sum of the given series by its first 6 terms. So, the sum of negative 1 raised to n plus 1 times 2 over n cubed from n is equals to 1 up to positive infinity. So, the solution, the given series converges by the alternating series test because, first, a sub n is equals to 2 over n cubed, which is greater than 0. Second, the limit of a sub n is equals to 0 as n approaches to positive infinity. And third, a sub n plus 1 is less than or equal to a sub n for all n since the quantity of n plus 1 cube is greater than n cube. Sum of the first 6 terms, we let n is equals to 1, 2, 3, and 4. As sub 6, sum of negative 1 raised to n plus 1 times 2 over n cubed from n is equals to 1 to positive infinity is equals to negative 1 raised to 1 plus 1 times 2 over 1 cube, that is equals to 2 over 1 cube, minus negative 1 raised to 2 plus 1 times 2 over 2 cube, that is 2 over 2 cube, plus the quantity of negative 1 raised to 3 plus 1 times 2 over 3 cube, that is 2 over 3 cube, minus negative 1 raised to 4 plus 1 times 2 over 4 cube, that is 2 over 4 cube, plus negative 1 raised to 5 plus 1 times 2 over 5 cube is equals to 2 over 5 cube, minus negative 1 raised to 6 plus 1 times 2 over 6 cube, that is 2 over 6 cube. Simplifying fractions into decimal, we have 2 minus 25 hundredths plus 74,074 millions minus 3,125 hundred thousandths plus 16 thousandths minus 9,259 millions. 2 minus 25 hundredths is equals to 1 and 75 hundredths. Plus 74,074 millions minus 3,125 hundred thousandths plus 16 thousandths minus 9,259 millions. 1 and 75 hundredths plus 74,074 millions is equals to 1 and 824,074 millions. Minus 3,125 hundred thousandths plus 16 thousandths minus 9,259 millions. So 1 and 824,074 millions minus 3,125 hundred thousandths is equals to 1 and 792,824 millions plus 16 thousandths minus 9,259 millions. So 1 and 792,824 millions plus 16 thousandths is equals to 1 and 808,824 millions. So minus 9,259 millions, we have 1 and 799,565 millions. So S sub 6 is approximately 1 and 799,565 millions. Error bound by alternating series remainder. The absolute value of R sub 6 is less than or equal to A sub 7. Equals 2 over 7 cube, which is equals to 2 over 343. And that is approximately 5,831 millions. So the sum S lies between 1 and 799,565 millions minus 5,831 millions, and that is equals to 1 and 793,734 millions, and 1 and 799,565 millions plus 5,831 millions, and that is equals to 1 and 805,396 millions. So 1 and 793,734 millions is less than or equal to S, which is less than or equal to 1 and 805,396 millions. So the final answer is 1 and 799,565 millions.